Section 7.7, Transforming Exponential Functions. The essential question: how can I transform exponential functions? So please write that down. As you notice, I crossed off logarithmic. This year, we are not going to be teaching that. It is truly not in the standards. And so due to time, we're going to just teach you how to transform exponential functions. Who uses this? Psychologists can use transformations of exponential functions to describe knowledge retention rates over time. You can perform the same transformations on exponential functions that you performed on polynomials, quadratics, and linear functions. Here's a quick review of that. If we are going to move an exponential function up or down, that's going to have I'm trying to get my marker here. It's going to be this, the plus k. As you can see over here, we have an exponential function, y equals 2 to the x. Plus 3 means you move it up 3 after you graph the basic exponential function, 2 to the x. Here, down 6. A horizontal translation means, if you look over here, remember if it's x minus something, that's moving to the right, x plus something moving to the left. Remember, it's always opposite of what you think. So here's the trick. If you have an exponential function, y equals 2 to the x, and you have 2 to the x minus 2, that's the exponent instead of just 2 to the x, that's your hint to tell you you're moving either to the right or left. If it's minus, you're to the right. Here, to the left. Notice the difference between up and down and right and left. Up here, we still start with the basic exponential function, 2 to the x, and the plus 3 is on the back tail end. The minus 6 is on the back tail end. Here, the exponent changed. 2 to the x minus 2, 2 to the x plus 1. That's your hint you're moving right or left. All right, the next one, a vertical stretch or compression. We know that. That's when you have a number out in front. If your number is greater than 1, like 6, that is a stretch. That means you're stretching your graph away from the x-axis, and I'm going to demonstrate that today. Y equals 1/2, 2 to the x. That number out in front is less than 1, so that's a compression by 1/2. And I always say, always look at the absolute value of that number, because I'm going to talk about that now. Go back to yellow. Reflection, when you have a negative out in front, like this, that's reflecting over the x-axis. So up here, if there was a negative 6, it would still be a stretch by 6. That negative out in front would be reflect across the x-axis. If your x changes, so that means your exponent, instead of 2 to the x, it's 2 to the negative x, that's across the y-axis. Asymptote is a line that a graphed function approaches as the value of x gets very large or very small. We've talked about that. So here's the deal. Let's get, oops, trying to extend my page here. Exponential functions have horizontal asymptotes. I think we talked about that in 7.6 video. Y equals. Log functions have vertical asymptotes. X equals. So when I say horizontal, that's horizontal, but I'm doing something wrong because asymptote is dashed. And when I say vertical, that's what I mean by vertical. And it makes sense because exponential and log functions are inverses of each other. Remember, we saw that again yesterday in 7.6. Find an inverse, switch x and y, and solve for y. So that's what's happening here. The horizontal asymptote for exponentials, y equals. So therefore, obviously, because these are inverses of each other, inverse functions of each other, the log asymptote will be x equals. Example number 1. All right. So we have the function f of x equals 2 to the x minus 2. Well, I know my parent function is f of x equals 2 to the x. My asymptote is going to be y equals 0 on this one. There may be times where it is not y equals 0, and we will cover that. And it's basically because there's nothing added or subtracted out there. Transformation, because the exponent is changing and it's x minus 2, we're going to the right 2. And now we graphed both of these ahead of time. We graphed the parent function and the transform function. How do we find the y-intercept? All we do is set x equal to 0 and solve for y. So we have f of 0 is 2 to the 0 minus 2 is 2 to the negative 2. Well, that's 1 over 2 squared, which is 1/4. That's the y-intercept. So as you can see, the parent function is the blue function, and 2 to the x minus 2 means we're shifting it to the right 2. So it moved to the right 2. Example 2. All right, the parent function I switched the order on this. Yeah. The y-intercept. Set x equal to 0 and solve for y. So f of 0 equals 1/3. 5 to the 0. Anything to the 0 power is 1. So it's 1/3. That's the y-intercept. The asymptote is still y equals 0. And the transformation, because we have that 1/3 in front, that's going to be a compress by 1/3 and graph the parent and transform functions. So we're going to do something right now, but I want to talk about this first. So the parent function is the blue, and the transformed function with the 1/3 in front is the red. 1/3, that means compress. That means you're pushing this blue graph down towards the x-axis. So I want to do a comparison here. And on our calculator, we're going to graph this. I want you to do this with me right now, please. We're going to graph the basic parent function. And then we're going to graph the 1/3. And then we're going to graph a third one. Whoopsie. We're going to just put a 6 in front and because that would be a stretch. So this one is the parent function. This one is a compress by 1/3, and this one is a stretch by 6. So we grab out our calculator, and in the y equals button, we're going to type 5 caret x, and then arrow down. In the y2, I want us to type, I put the 1/3 in parentheses because I never know if I need to or not, and then 5 caret x, and then the y3 is going to be 6, and then this time let's put the 5 to the x in parentheses, just so the calculator knows. Don't multiply 6 times 5. It's 5 to the x, and times 6 means you are stretching it. And let's graph it. And let's talk about what's happening. I'm going to probably have to change my window, so just be patient with me here. Okay, this is twirling. I should have changed my window ahead of time here. Okay, I am going to go to my window just so we can see this better. I'm going to change that to -10. I'm going to change that to 10. Just the basic window where your x min is -10, your x max is 10, your y min is -10, and your y max is 10. And I'm going to hit graph. All right, I just want to demonstrate what's happening here so you understand the difference between compress and stretch. All right, so the blue function is our parent function, 5 to the x. The red function is our compressed function, 1/3 by 1/3, and the black is our stretch. So notice the difference in how they look. The blue is obviously in the middle. The red is the compressed. That means I'm pushing the blue down, compressing it down towards the x-axis. The black, I'm stretching the blue away from the x-axis. And it's always you're changing your parent function. I just want to go back 1 minute here. Okay, that's what I wanted to mention. So a lot of times I should add one little piece here because yes, compressed by 1/3 is fine for me, but a lot of times we don't do horizontal compressions and stretches in Algebra 2, but I want to make sure when you see this, you understand. It's truly a vertical compress. I should have added that word by 1/3. A vertical stretch by 6. So up here, I should have said this was a vertical compress. All right. Example 3, I'm going to save that for class. And I just want to read through this. Because a log is an exponent, transformations of log functions are similar to transformations of exponential functions. We can stretch, reflect, and translate the graphs of the parent logarithmic function, f of x equals log base b of x. And the transformations of ln work the same way, because ln of x means log e of x. However, we are not doing transformations of logs and natural logs, so you can cross that off. And on example 5, you can cross off this one and you can cross off this one, and we only are going to do this one right here. So now it's giving us the parent function, and it's saying it's reflected across both the x and the y-axis, across both axes, and moved 2 units down. And it wants us to write the transform function. So let's do that right now. Well, If it's reflected across the x-axis, there's a negative out in front. If it's reflected across the y-axis, the negative is attached to the x, and then it's moved down too. It's that basic, and that's it. And there are no video questions for today.